This is part 2. In the previous lecture, I mentioned that the expected value of the ut, its error term, it's equal to 0, or expected value of epsilon t, it's equal to 0. So now variance of ut, what will be the value of variance? It's equal to expected value of ut square, it's equal to expected value uh, third bracket, and epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus up to rho epsilon uh, rho power s epsilon t minus s bracket close, and whole of square. So expected value of epsilon t square plus rho square epsilon t minus 1 square plus rho power 4 epsilon square t minus 2 plus up to 2 rho dot 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 plus 2 rho epsilon t expected value of t minus 1 plus dot 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 bracket close. And we know that the expected value of epsilon t square is equal to sigma epsilon square plus expected value of rho square epsilon t minus 1 square, here rho square in the outside, and expected value of epsilon t minus 1 square, it's sigma epsilon square plus rho power 4 sigma epsilon uh, sigma epsilon square plus dot dot dot. The homoscedasticity assumption is hold here, that is why expected value of epsilon t square is equal to expected value of epsilon t minus 1 square plus expected value of epsilon t minus 2 square. So sigma epsilon square common, and in the third bucket there is 1 plus sigma 1 plus rho square plus rho power 4 plus dot dot dot, it's continue actually, and sigma epsilon square, and the bracket term that we can write in this way, that 1 by 1 minus rho square, that means 1 plus rho square plus rho power 4, the formula is 1 divided by 1 minus rho square. So this is the value of the variance of ut, and now find out the covariance of ut minus 1. We know that covariance is not equal to 0. So expected value of epsilon t plus rho epsilon t minus 1 plus dot 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 continue, and expected value of t minus 1 plus rho epsilon t minus 2 plus dot 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 continue, it's equal to 0 plus expected value of rho epsilon square t minus 1 plus rho cube expected value of epsilon square t minus 2 plus, so rho sigma epsilon square plus rho power 3 sigma epsilon square plus dot dot dot, it's continue, and sigma rho sigma epsilon square common, and in the third bucket there is 1 plus rho square plus rho power 4 plus dot dot dot, rho sigma epsilon square into 1 by 1 minus rho square. We know the formula, that is coming from 1 plus rho square plus rho power 4, it's the formula, it's the value of this 1 divided by 1 minus rho square. And in the first order autocorrelation coefficient, it's correlation between ut minus 1, is covariance ut minus 1, standard deviation of ut and standard deviation of ut minus 1. We know the value of covariance and standard deviation. The value of covariance divided by variance, standard deviation of ut and standard deviation of ut minus 1 is also, we can write variance. So putting the value here, variance and covariance. Variance is sigma epsilon square 1 minus rho square, and covariance is sigma rho into sigma epsilon square 1 minus rho square. This two term is cut down, and also the epsilon sigma epsilon square also cancel out, and then get rho 1, rho superscript 1. So Sth Weather correlation coefficient will be correlation between ut minus s is equal to covariance of ut comma ut minus 1 and variance of ut. So covariance of ut minus s is equal to rho s sigma epsilon square 1 minus rho square, and variance of ut it's equal to sigma epsilon square divided by 1 minus rho square. These two term cancel out, and finally get rho superscript s. Now find out the value, find out the dispersion matrix of u, that is expected value of u prime, it's equal to, there is all the variance terms same, but covariance terms are different. This is the matrix format, and if sigma epsilon square 1 minus rho square common, then the whole matrix is 1 row square up to row n minus 1, and the second row 1 up to it's continue and up to row n minus 2, and in the last row, that is row n minus 1, row n minus 2, and it's the last value is in the matrix is 1. And this can also consider as omega, so we can write that sigma u square omega. If rho and sigma u square are known to us, we can easily determine the dispersion matrix of u, and if omega inverse is equal to 1 by 1 minus rho square and multiplied with the matrix, that is 1 minus rho, and the other rest of the values are 0. In the second row, minus rho 1 plus rho square minus rho, and rest of the terms are 0. And in this way the last row is 0, first column 0, second column 0, third column as well as 0, and the last three columns are 0, minus rho and 1. So we get beta hat GLS, it's equal to x transpose omega inverse x whole inverse x transpose omega inverse y. It is same like beta hat VLS, that is x transpose x inverse x transpose y, but here omega inverse, this term is extra. If we use direct GLS technique, the process will be too much cumbersome, so we use 2SLS technique to overcome this ambiguity. To avoid the cumbersome method of direct GLS technique, we use 2SLS, two-stage least square technique, to estimate the parameter and a non-spherical model where only autocorrelation with heteroscedasticity exists. Autocorrelation but homoscedasticity exists. Here use not the GLS but use the 2SLS, because to avoid the cumbersome method. Only autocorrelation with homoscedasticity exists, then y is equal to x beta plus u, expected value of u is equal to 0, expected value of ut and ut minus s, that is autocorrelation successive value ut minus s equal to gamma s, and expected value of ut square, that is variance, is equal to gamma 0. So expected value of ut minus s is a covariance term, and expected value of ut square is a variance term. Variance is gamma 0, covariance is gamma s. If we use the 2SLS techniques, we first make the non-spherical model to spherical model by using some transformation matrix, that is rho, and here the occurrent transformation matrix PC rho C it's used. The rho C